You know that feeling when you're just staring out a window, completely zoned out, lost in thought? For the longest time, we thought of the brain purely like a machine. Input goes in, output comes out. But what happens when you're just idling? In this explainer, we're diving straight into exactly what your brain is up to during those quiet moments, and how a concept called functional connectivity literally changed the game for how we understand the human mind.
We've got a great roadmap for this explainer. We'll hit the mystery of the idle brain, define functional connectivity, and unpack the famous default mode network. Then, we'll weigh the strengths and limitations of this method, and finally, tackle how we actually prove cause and effect in the brain. Let's get to it.
So, what actually happens up there when you're doing absolutely nothing? It's a wonderfully simple question, right? But asking it accidentally sparked a total revolution in modern neuroscience. Because as it turns out, your resting brain, it is incredibly active and surprisingly organized.
Which brings us to Section 1, the idle brain mystery. For years, the gold standard in neuroimaging was all about the task. Researchers would put someone in an fMRI or PET scanner, give them a specific job, like reading a word or tapping a finger, and literally just watch to see what regions lit up compared to a resting baseline. But they kept noticing this really weird, persistent pattern. Certain areas of the brain would consistently shut down the second a subject actually focused on the outside world. Basically, whenever the task started, these specific regions just went completely quiet.
In early brain scans, mapping these patterns revealed something pretty incredible. At first, researchers labeled these areas task-induced deactivations. They figured, hey, maybe these parts of the brain are just powering down to save energy, right? Well, actually, scratch that. The reality was the exact opposite. These specific regions were firing on all cylinders when subjects were simply resting, daydreaming, or just letting their minds wander. The brain wasn't turning off at all. It was just shifting gears into a totally different, internally focused mode.
Moving on to Section 2, defining functional connectivity.
So how do we actually measure this hidden activity? We use something called functional connectivity. In science terms, that's the measurement of low-frequency, spontaneous correlations in the brain's intrinsic activity. But let's break that down. We typically track this using fMRI to measure the BOLD signal. That stands for blood oxygen level dependent signal. In plain English, we're basically just watching the slow, rhythmic waves of oxygen-rich blood flowing through the brain while someone lies there doing absolutely nothing.
To actually map these networks out, researchers follow 3 steps. First, they pick a starting point, which we call a seed region. Second, they track the spontaneous ups and downs of blood flow in that seed over time. And third, they run a statistical correlation across the entire rest of the brain. They are hunting for other regions that are pulsing in that exact same highly similar pattern.
Think of it like being in a dark room listening to a massive choir. Even if you have no idea what song they are singing, if the sopranos on the left and the altos on the right raise and lower their voices perfectly in sync, you can pretty confidently guess they're reading from the exact same sheet music. It's the same in the brain. If the variation of activity in one specific region perfectly matches the variation in another, we infer that they're functionally connected. They are part of one common interacting network.
All right, Section 3, the default mode network.
Now this is where it gets really cool. When researchers compared those early deactivated regions with the new functional connectivity maps, they found an absolutely perfect match. By placing a starting seed in a major hub like the posterior cingulate cortex, the resulting map completely mirrored the exact areas that went quiet during active tasks. They'd essentially mapped the exact same system from 2 totally different angles. And today, we know this famous system as the default mode network.
And we know for sure that this network isn't just random idle noise. When you check out of the outside world, your default mode network kicks into high gear for internally focused cognition. It's the network that fires up when you're retrieving childhood memories, daydreaming about your plans for the weekend, or trying to put yourself in a friend's shoes, what psychologists call theory of mind. It is literally your brain's built-in engine for self-reflection and mental simulation.
Let's jump into Section 4, strengths of the method.
As a research tool, resting state functional connectivity brings some massive advantages to the table. For one, it maps the brain's large-scale architecture completely non-invasively. But the real game changer is that it requires absolutely zero active task execution. The subject literally just lies still. This is absolutely crucial for clinical settings. It means we can map the brain networks of infants or patients with severe cognitive disorders like Alzheimer's or schizophrenia who might struggle to follow complex instructions. We can identify critical functional hubs purely by tapping into the brain's baseline rhythms.
But to be fair, we have to look at Section 5, weaknesses and limitations.
Because to be rigorous scientists, we can't ignore the limitations here, and there are three big ones. First up, fMRI is an indirect measure. We're looking at sluggish blood oxygen changes, the hemodynamic response, not the lightning-fast electrical firing of the actual neurons. Because of this, it has pretty poor temporal resolution. We're getting data in seconds, whereas the brain actually operates in milliseconds. And finally, it's highly susceptible to physiological noise. I mean, just taking a deep breath, a tiny head twitch, or a minor scanner hiccup can create false correlations in the data, so you have to be super careful.
Which perfectly sets up Section 6, proving cause and effect.
This brings us to the ultimate limitation of functional connectivity, and honestly, the golden rule of all scientific research: causality versus correlation. Listen, if two brain areas sync up their blood flow perfectly, yes, we know they are functionally connected. But we do not definitively know if Area A caused Area B to activate, or if some hidden Area C is secretly pulling the strings for both of them. Functional neuroimaging by itself cannot prove causality. It only shows us the correlations.
So what's the solution? To truly prove causation, to establish that a brain region is actually necessary for a specific cognitive function, we have to safely perturb the brain. We have to poke the system. Modern neuroscientists do this by combining fMRI with tools like transcranial magnetic stimulation, or TMS. By temporarily disrupting or enhancing a targeted region, and then watching the ripple effects in both the network's connectivity and the person's behavior, that is how we finally bridge the gap. We move from mere correlation to actual hard proof of causation.
And that leaves us with a pretty profound final thought to wrap up this explainer. We've mapped the default mode network. We've seen that our deepest internal thoughts, our memories, and our future plans are somehow reflected in the synchronized pulsing of blood across these regions. But as we keep pushing the boundaries of functional connectivity and start using new tools to prove causation, it really makes you wonder, as we map the edges of the brain's idle networks, are we genuinely getting closer to finding the physical seat of human consciousness, or are we still just watching shadows on the wall?